This video is on section 7.4 notes, the trigonometric form of complex numbers. So as a reminder, a complex number is a number that is denoted a plus bi, where a is the real part of the number and bi is the imaginary part of the number. And this section in the textbook assumes that you've learned about complex numbers before and that you're familiar with them and remember what you've learned. So you know that I is the square root of -1. You know that I squared is -1. You know how to add complex numbers. You know how to multiply complex numbers. You know how to subtract them. You know how to divide them. Just that this is not an introductory lesson to complex numbers. This is a little bit of like a part 2 from maybe what you've learned in high school. So it says the complex plane, so we're going to be graphing complex numbers first. It says the complex plane provides an order to the complex number system and allows us to treat complex numbers like vectors, to treat them like directed line segments. So if we look at this, we can see that the real axis is the x-axis and the imaginary axis is the y-axis, and that when we graph them, we just graph the real number first and the second number, the imaginary number second. So the complex number 2 plus 4i would be right 2 up 4. The complex number -3 minus 2i would be left 3 down 2. And then we have something called the absolute value of a complex number, which is kind of an abstract idea, but the definition of it is just the distance between the complex number that you've graphed and the origin. So if you look at this now, we can think of it as like you're drawing a triangle, you're making a right triangle, and this would be the hypotenuse of the right triangle. So you're seeing this formula, the square root of a squared plus b squared, and you'll notice we've already seen this formula, it was in the last section, and we're actually going to see it again in this chapter before we're through with the chapter. So this is going to be kind of a significant formula in a few different contexts that are different but are all related. Okay, so here's a couple example problems. They want us to graph the complex number and then to find its absolute value, which means to find the distance between the graphical form of the complex number and the origin. So 3 plus 4i would be right 3 up 4. So there's 3 plus 4i. The absolute value is the distance between this and the origin. So the absolute value of 3 plus 4i is the square root of 3 squared plus 4 squared, which is the square root of 9 plus 16. That's square root 25, which is 5. So this is a distance of 5 away from the origin. Next, we have the complex number -2 minus I, so left 2 down 1. And to find the absolute value of -2 minus I, we're just going to do the square root of -2 squared plus -1 squared. So that's the square root of 4 plus 1. So that distance is the square root of 5, a little bit more than 2. All right, on the next page of notes, we're going to start to talk about the trigonometric form of a complex number. And this is where you're really going to start to see it feel a little bit more like what we learned about when we talked about vectors. So it said a plus bi is a complex number. The trigonometric form of z, if z is the complex number, is r times cos theta plus I sine theta. So you'll notice that's identical to one of the forms of a vector, where r is the absolute value of a complex number, and theta is the angle and standard position whose terminal side contains the point AB. So an abbreviation for this is r cis theta. And you don't have to use the abbreviation, but you know, it could be good. So r is the modulus, that's what they call it here. R is the modulus of a plus bi. In vectors, we called it the magnitude. So r is the modulus of a plus bi. Theta is the argument. Of a plus bi. In vectors, we called it the position angle. All right, so modulus and argument, just same idea, but slightly different words to describe it. All right, so here what they've done is they have graphed the point AB. This is representing the complex number a plus bi. And they've labeled r here. This is the modulus, which is the absolute value of this complex number. So I'm going to go ahead and label this in the picture. This is the absolute value of a plus bi, or the modulus. Okay. Here's the angle that is created if you look at the positive x-axis, and then this side, the angle in standard position, whose terminal side contains the point AB. So that's what they were talking about when they described this up here. So this is the angle that's being created. And so I'm going to go ahead and write these formulas down. So these are in our notes, and this is just something we can refer back to. So the modulus, remember, just like we worked out on the previous page, is the square root of a squared plus b squared. So that's the modulus. It's also the absolute value of a complex number. Now, if we look at this triangle that we drew, we can see here's the angle. This would be the opposite side. This would be the adjacent side of the triangle when we look in comparison to this angle. And then, of course, over here we have the hypotenuse. So if I look at this picture, then if I wanted to find cos of this angle, I would say that cos theta is adjacent over hypotenuse, is a over r. And sine theta is opposite over hypotenuse, which is b over r. And so if I wanted to find the real part of the complex number, I would say that cos theta multiplied by r is the real part of this complex number. If I wanted to find the imaginary part of the complex number, I would say that r times sine theta is the imaginary part. And this should feel somewhat familiar because we looked at this exact picture, but we just talked about the vertical component of a vector and the horizontal component of a vector. And aside from that, we found them the same way. So now we're going to say that a plus bi, a complex number, is the modulus times cos theta plus I sine theta. And remember that this right here can be abbreviated r cis theta if you don't want to have to write out everything. Okay, so one thing we want to make note of says, this note up here says, since there are infinitely many angles whose terminal side contains AB, so remember back to what we've been learning as we've done the unit circle and looked at angles, is that you always have coterminal angles that end up in the same spot. So if this was a 30-degree angle, you could also call it a 390-degree angle. You could also call it a negative, I can't do that math in my head that fast, but you understand the idea, negative 330-degree angle. So there's infinitely many ways we could describe this angle, but when we do the trigonometric form of the complex number, we are not going to write a bunch of different angles. We're always going to use the smallest positive value, the smallest non-negative value of theta that we can find. Okay, so just think about when you're doing these problems, you're always going to look for whatever number's on the unit circle. The very smallest positive angle that you can find is the one that you're going to use. Okay. All right, so now we're going to take these complex numbers and we're just going to write them in their trigonometric form. So, and I put it on here again so you could graph them, even though at this point graphing is going to be pretty easy for us. So -2 square root 3, I'm not going to be able to graph that off the top of my head, so I'm just figuring out what the decimal is. So this is going to be left about 3.5. So left 3.5 and up 2. Okay, so that's where this complex number is. And so I'm going to go ahead and figure out the modulus. So this is the square root of -2 square root 3 squared plus 2 squared. So -2 squared is 4. 4 times 3 is 12. So this is the square root of 12 plus 4, which is the square root of 16, which is 4. Okay, so the modulus is 4. The distance between this and the origin is 4, or the square root of that complex number, that's 4. And so now I can go ahead and find the angle that is made between, I'll go ahead and draw this. Now I'm going to go ahead and just find this angle right here. And so this should be still reminding you of the last set of notes that we did. And so I'm actually going to find it the same way. I'm going to do tan theta, just like we did with vectors, and I'm going to do y divided by x, or the vertical component divided by the horizontal component. So the vertical component is that I went up 2. The horizontal component is that I went left 2 root 3, -2 root 3. So tan theta is, I'm going to cancel the 2's, 1 over negative root 3. So now I'm going to picture my unit circle, and I'm going to imagine where in quadrant 2 on the unit circle do I have a y coordinate divided by an x coordinate that gives me 1 over negative root 3, which I know simplifies to negative root 3 over 3. So where on the unit circle do I get negative root 3 over 3? In the second quadrant, that is at 5 pi 6. So in quadrant 2, this is 5 pi 6. Okay, so now I can go ahead and write my complex number in trig form. So I'm going to say -2 square root 3 plus 2i in trig form would be the modulus for times cos 5 pi over 6 plus I sine 5 pi over 6. Okay, and I'm going to go ahead and write a note up here because I didn't put this in my notes up here. I'm going to write find theta using tan theta equals y divided by x or b divided by a. So find the theta by using tan. And honestly, if you've drawn this triangle, if you don't want to use tan because that's harder to recognize on the unit circle, this was 2, this was left 2 root 3. You could always actually label out your triangle and put 4 as the hypotenuse. And if you know that 4 is the hypotenuse, then we could have done sine 2 over 4, or we could have done cos -2 root 3 over 4. So you can always actually draw all 3 sides of the triangle and then choose which trig function you want to use each time. But for consistency's sake, as I go through examples, and this is throughout the whole chapter, I'm going to use tan because we typically in the problem have the vertical component and the horizontal component, or the b and the a. We typically have those numbers that we can easily divide. And so I'm going to consistently do that just so we can get used to it. But if you want to do one of the other trig functions, that's fine. All right, so for this one, we have right 3 down 2. And I can think of this as a triangle if that would be helpful for me if I want to use one of the other trig functions. I'm going to find my modulus. That's the square root of 3 squared plus -2 squared. So we have 9 plus 4, which is the square root of 13. So there's the modulus. And then to find the argument, which is the angle, to find the angle, I'm going to say the vertical component divided by the horizontal component, or the b value divided by the a value. So -2 divided by 3. And this is one that is not on the unit circle. And since it is not on the unit circle, that means it's a calculator problem. So we are dealing with degrees in this chapter for the most part, unless a problem really specifically states that it should be radians. And so I'm going to switch my calculator into degrees because I'm going to have to hit tan inverse to solve this. And so now I'm going to do tan inverse of -2/3. And I know that my degree should be in quadrant 4. And in quadrant 4, we have to keep track of this note that they said we want to use the smallest non-negative value. So we have that theta is approximately -33.690 degrees, and this is in quadrant 4 already, but this is a negative value, and they always want us to choose values that are on the unit circle. So if I want to find the angle that is coterminal with this, I'm going to go ahead and just add 360 degrees. If this had been in the wrong quadrant, if I needed to find another answer for tangent because this was in the wrong quadrant, I would add 180 degrees. But this was in the correct quadrant, it just wasn't positive. So I'm going to go ahead and make it positive by adding 360 degrees, and I get 326.310. And now I can go ahead and write this complex number in that trigonometric form. So I'll write it up here. I'm going to say the modulus square root 13 cos 326.310 plus I sine 326.310. And so here is our complex number in the trig form. Okay, I want to address something before it could be a point of confusion because I just realized that I did this without even thinking. This problem I did in degrees, but this problem I obviously did in radians. And so here, because we're not dealing, well, we are dealing with triangles, but because I didn't use my calculator on this one, and there's nothing in here that explicitly tells me what type of answer I have to have, it technically doesn't matter. I was just trying to say, let's do a degrees. On this one, I was trying to say, let's keep our calculator in degrees because we've done everything in degrees for this unit. For problems like this, I would check with whatever my math lab says for what form they want the answer in. And if they don't say what form, or if I was to give you a quiz or a test and I did not specify if I wanted it in radians or if I wanted it in degrees, then technically both answers should be correct. You should be able to say 5 pi 6 or say, what is that, 150 degrees? You should be able to say both of those and still get full credit. And then the same thing with this, you should be able to say 326.310 or be able to say the radian equivalent and get full credit. So I didn't mean to be confusing here. I just noticed myself that I did that on my notes. But I would pay attention to the instructions, which one they say to do. And if they don't specify, then that means it's okay for you to choose, but you want to make sure that whatever you're doing, you are using the correct mode in your calculator so that the mode matches. And then here, be especially careful that if you are doing degrees, you're always putting that little degree bubble in there, because if you ever don't put the bubble, it means you're writing a radian answer, even if that's not what you meant to do. So be careful of that. All right, on the next page, they want us to backtrack. So they're giving us a trigonometric complex number, and they want us to write it in the standard form, a plus bi. And this is kind of the nicest form to convert between, because all you have to do is take the modulus and distribute it, and then just simplify. So for this one, we're going to be able to write the answers in exact form because I know that pi fourths is on the unit circle. For this one, we're going to have to write decimals because 143 degrees is not on the unit circle. So I'll go ahead and do this one first. I'm going to have a square root of 2 cos pi fourths, that's the a, the real number, root 2 times sine pi fourths, and I'm just going to stick the I on the end because this is all going to end up being the coefficient for the I. So I'll go ahead and do that multiplication. Root 2, cos of pi fourths is root 2 over 2, and then we have root 2. Sine of pi fourths is also root 2 over 2, and then the I is going to be on the end. So root 2 times root 2 is just 2, so we have 2 over 2. So that's 1 plus 1i, or 1 plus I. So this is the complex number in standard form. This is the exact same thing in the trigonometric form. It looks different, but they're identical. Okay, over here, we've got 3.6 cos 143 degrees, and then 3.6 sine 143 degrees, and I'll put the I on the end. And then for this one, we're just going to type it into our calculator, making sure that our calculator is in degrees. And so this one, negative 2.875 plus 2.167i. All right, so next we have the product and quotient of complex numbers. So since z represents a complex number, and that's pretty common to use the letter z as the variable that represents a whole complex number, here they're going to have z sub 1 as the first complex number, z sub 2 is going to be the second complex number, and then they're going to give us two formulas. They say if you multiply the two complex numbers together, here's the formula. If you divide the two complex numbers, here's the formula. So if you multiply the two complex numbers, then you take each modulus and you multiply them and you put them in the front, and you take each argument, you take the angles, and you add them together. If you're dividing, you take each modulus and you divide them, and you take each argument, you take the angles, and you subtract them. All right, so it says we're going to go ahead and we're going to find the product, and we're going to find the quotient for each of these two trigonometric complex numbers, or complex numbers in that trigonometric form. And then it's going to make it a little bit more complicated. They want us to take those values that are in the trigonometric form, and when we actually do the computation, we're going to get the answers in trigonometric form. They want us to take those answers when we're done and express them in a plus bi. So they want us to convert it back to the standard form when we're done. Okay, so up here I'm going to say z sub 1 times z sub 2, and I take the modulus from each, 6 and 2, and I'm going to multiply them together, 6 times 2. And then I'm going to take cos, and I'm going to add the angles together. And I can tell that those angles are in radian form because they do not have little bubbles. So 2.4, 1.8, for multiplying, I add them together. So 2.4 plus 1.8. Okay, so z sub 1 times z sub 2 is 12 cos 4.2. I don't need the parentheses. Cos 4.2 plus I sine 4.2. Okay, so this is the trig form of the answer. We have found the complex number, the product of the complex numbers, and we've written it in trig form. Now we're going to go ahead and we're going to write it in the standard form, the a plus bi. So in the standard form, I get 12 cos 4.2 plus 12 sine 4.2. I'm going to put the I on the end. And then I'm going to go ahead and actually see what that gives me. Since we're talking in radians now, I have to change my mode into radians. So 12 cos 4.2 and then 12 sine 4.2. And so this is the product. So trig form, and this is the standard form. Okay, we'll go ahead and we'll do a similar process to find the quotient. So the first complex number divided by the second complex number, we will do the first modulus divided by the second modulus, cos the first argument minus the second argument. So 3 cos 2.4 minus 1.8 is 0.6. And so we just found the quotient, and we have the trig form of the quotient. And now we can go ahead and distribute that modulus so that we can get the standard form. So 3 cos 0.6, 3 sine 0.6, I'll stick the I on the end. Again, I know this is in radians because there was no degree bubble. And so I'm calculating this while my calculator is in radians. All right, now they're going to make it a little more complicated. They're going to give us two complex numbers just like before, but when they give us the complex numbers, they're going to give us the complex numbers in that standard form. And in the standard form, they're going to say find the product and find the quotient. But our product and quotient formulas are in the trig form. So we need to convert these into the trig form to find the answers. Now here, in reality, they probably should have specified what format they want the answer to be in, but typically in math practice, unless they give you a specific format, which is what happened in the last example, you should match the format of the problem. So since they gave the problem to us in standard form, we should probably give the answers in standard form. In the last problem, if they gave us the problem in trig form, we would give the answers in trig form. And the only reason we didn't was because they told us to give it to them in a different form. So here the instructions say use the trig form to find the product and the quotient, and so we're going to go ahead and do that. So z1, z sub 1 is negative 2 plus 2i square root 3. And one of the reasons they specified use the trig form is because in high school, we learned how to find the product of complex numbers, and we learned how to find the quotient of complex numbers, and we can do that from the standard form. So we are learning something in addition to what we've done in high school, and Honestly, if we were in high school math, I probably would still be doing it the high school way. The only reason I'm doing it this way is not because it's easier, is only because they said we had to. Okay, so here we've got this. We have to put it in the trig form, and so I'm going to find the modulus first. So I'm going to say r is the square root of -2 squared plus 2 root 3 squared. So we have 4 plus 2 times 2 is 4. 4 times 3 is 12. So this is the square root of 16, which is 4. So the modulus for this one is 4, and then tan theta is 2 root 3 over -2. So this is negative root 3. Okay. And if I think about this, if I think about graphing this, I would have gone left and then up. Left to up to root 3. And so if I went left and then up, that means I'm looking for an angle that's in quadrant 2. Looking for an angle that's in quadrant 2. So now I'm picturing the unit circle. I'm imagining where we have a y-coordinate divided by an x-coordinate that simplifies to negative root 3. And I'm looking for that in quadrant 2. And the place where that happens is 2 pi thirds. Okay, so I know that I don't want to run out of room, so I'm going to write it up here. I know that the trig form for my first complex number is going to be 4 cos 2 pi thirds plus I sine 2 pi thirds. And if you wanted to, honestly, you could be doing this in degrees. You don't have to do it in radians. They never said you had to do it in radians. Okay, so next we have the second complex number, which is root 3 plus I. And so first I'm going to find the modulus. So root 3 squared plus 1 squared. So that's 3 plus 1, which is the square root of 4, which is 2. Okay, so the modulus is 2. And then we have tan theta is 1 divided by the square root of 3, which is root 3 over 3. So I know that if I were to graph this complex number, I would go right root 3 and up 1. That places this in quadrant 1. So I'm looking for an angle that's in quadrant 1. I'm looking for where on the unit circle the y-coordinate divided by the x-coordinate simplifies to root 3 over 3, specifically in quadrant 1, and that would be pi over 6. All right, so my second complex number had a modulus of 2 cos pi over 6 plus I sine pi over 6. Okay, so now I can go ahead and I can use the product rule and the quotient rule, or not the product rule and the quotient rule, the product formula and the quotient formula to figure out what these answers will be. So if I multiply the two together, then I just take the modulus of each and I multiply them. So 4 times 2 cos, and then I add the angles together. So 2/3 and 1/6 would be 5 pi 6 radians. Let me show my work better. Since these are my notes, I'm going to make sure that I'm showing my work well so that when I look back at my notes, I know what I did. So I'm going to write 2 pi thirds plus pi 6. And then I'll go ahead and write what I actually got. So 4 times 2 is 8, and this was cos 5 pi 6. Cos 5 pi 6 Okay, so here's our trig form, and we're going to have to write it in that standard form. So I have 8 cos 5 pi 6 plus 8 sine 5 pi 6 5 pi 6 on the unit circle, cos would be negative root 3 over 2. So this is 8 times negative root 3 over 2. Sine of 5 pi 6 is 1/2. So 8 divided by 2 is 4. So we have negative 4 root 3 plus 4i. Okay, so there's our product. And now we just have to do the quotient. So 4 divided by 2, cos 2 pi thirds minus pi over 6. So there's our quotient. And now I'm just going to simplify what I have. So 2 cos that's 1/2. 2/3 minus 1/6 is 1/2. So 2 cos pi halves plus 2 sine pi halves. Cos of pi halves is 0. Sine of pi halves is 1. So we have 0 plus 2i, which is just 2i. So this is a complex number that happens to only have an imaginary part. It does not have a real part. So here's our product. Here's our quotient. All right. And then last in the notes, we want to talk about complex conjugates. So the complex conjugate of a plus bi is a minus bi. The product of the complex conjugates is a squared plus b squared. And I'm going to go ahead and show you the work for that over here off to the side. So if I did a plus bi times a minus bi, if I multiply the complex number by the complex conjugate, I have to FOIL these out. So I have a times a is a squared. A times negative bi is negative abi. Bi times a is positive abi. And then positive bi times negative bi is negative b squared I squared. So these two terms cancel out, which always happens whenever we have conjugates. The two middle terms always cancel out. And then one thing we have to remember from when we first learned about complex numbers is that I squared is negative 1. So I think I mentioned at the beginning of the video that I is the square root of negative 1. I squared is negative 1. So this is negative b squared times negative 1, which makes this a squared plus b squared. And what you'll notice is that if you take a complex number and multiply it by its conjugate, you get a squared plus b squared, which is a real number. There's no imaginary portion anymore. All right. So next, if we look at the complex conjugate of this, it's a little bit counterintuitive. You can't put a minus here in the middle because whenever we write these the trig form of a complex number, we have to have a plus in here. So the way that they write this instead is we use what we know about co-function identities from trig. So we actually end up writing it as r cos of negative theta plus I sine of negative theta. And that's kind of a tricky way to be able to write this so that there's still a plus in the middle. We know that cos of negative theta is just cos theta, so that didn't really change anything. But sine of negative theta is actually negative sine. So what we did is we kind of tricked it so that we would change the sign in the middle, but we still have angles that are matching here. All right, so now that we have the formula of the complex conjugate, let's use that formula for this next example. It says find the product of this complex number and its conjugate. And we're going to use multiplication in the trig form. So if this is the complex number, then its complex conjugate would be 2 cos negative pi thirds plus I sine negative pi thirds. And if we're using multiplication in the trig form, then we can go ahead and multiply. We would just take the modulus of each and multiply those together. So 2 times 2 cos, and then add the arguments together. So pi thirds plus negative pi thirds plus I sine pi thirds plus negative pi thirds. And so the arguments, or the angles, are just 0 radians, or you could say 0 degrees. It doesn't matter in this case, but it's 0. So we have 4 cos 0 plus 4 sine 0 I. And you could leave this in the trig form and just say this is the answer, but I want to show you what it looks like in the standard form, just so you can fully appreciate what's happening when you multiply a complex number times its conjugate, so that you can see that what happened here, that a plus bi times a minus bi, how it became a squared plus b squared. I want you to be able to see that here too. So 4 times cos 0 would be 4 times 1. 4 times sine 0 would be 4 times 0. And so that just gives us 4. So if we think back to our formulas, 4 is the modulus, right? 4 is the square root of a squared plus b squared. And so if the product of a complex conjugate is a squared plus b squared, then we should always just end up with this number in the front here. This is always going to happen because your angles are always going to become 0 when you multiply a number in its complex conjugate in the trig form. When you multiply the complex number in its complex conjugate, those angles are always going to cancel out, and so this is always going to happen, and we're always just going to end up with this number in the front here. So it doesn't matter which form you multiply in. You could multiply this and get a squared plus b squared, or you could multiply this and its complex conjugate, and you're going to get a squared plus b squared. Whichever form you use doesn't matter. And that's the case also, and this is what I mentioned before, is we can multiply these in trig form, which is what we did here, and we're going to get an answer. But if you did not convert these in the trig form, if you did it the high school way and just took this in standard form and this in standard form and multiplied them, you'd still get this answer. Or if you took this from the way we used to do it in high school in standard form and divided them, you'd still get the other answer. So we're just learning kind of a more complex way of doing it, tying in the trig form, because that's the context of the unit that we're studying right now. So this is part 2 of complex numbers. We're carrying it along from high school and we're getting a deeper understanding.